In this chapter, we'll look at use of atomic classes in multi-threaded applications. Consider an multi-threaded application that is required to track website activity. In very simple terms, it needs to maintain a count of page visits. We can have a website activity class that have integer counter, and we can provide an helper method increment that will increment the integer counter. Since we can have page widgets simultaneously, this could lead to race condition when they try to invoke the increment method. Hence, we have to protect this increment method using synchronized keyword. By using synchronized keyword, only one thread will be able to invoke the increment at any given point in time. So use of synchronized keyword is expensive with respect to performance, since it has to acquire the lock as well as release the lock. A better alternative is to use atomic classes. So it will give better performance as compared to synchronized. Let's take a close look at what are atomic classes and how they function. Atomic classes use compare and swap instructions supported by CPUs to achieve synchronization. CAS is done in 3 steps. First, it gets the current value. Then it compares this value with V1. If it is same, then the current value is updated with the value V2. Else, it does nothing. Here is a sample implementation for CAS. It is returning a boolean and it is accepting 2 values, V1 and V2. First, it will compare the current value. So it is fetching the current value using get and it is comparing it with V1. If this is true, then it is calling set operation and it is passing V2 to the set and is returning true. If the current value is not matching V1, then it is simply returning false. This is a very simple implementation of CAS. So what are atomic classes? Atomic classes are wrapper classes around primitive data types. They are part of Java util concurrent atomic package. Examples of atomic classes are AtomicInteger, atomic boolean, atomic long, atomic reference. The operation on them are guaranteed to be atomic. They are safe to be used in multi-threaded environment. Here is a snippet that shows a simplified implementation of get and increment. It has the below steps. It first gets the current value using get method. Later it calls compare and set method, passing x and x plus 1. As we discussed earlier, compare and set will return false if the current value is not x. Else it will set the current value to x plus 1 and then return true. So in this case, the loop is going to exit only when it is successfully able to increment the current value to current plus 1. If multiple threads call get and increment, only one will succeed, while others will continue to run in a loop. Hence, this method can be called in multi-threaded environment without needing locks. Now, as a result of this, they give better performance as compared to using locks or synchronized keyword. Let's take a look at 2 demo examples. In the first demo, we are going to be having 100 threads that will increment a variable 1 million times using AtomicInteger. In the second demo, the functionality is same, but we'll be using synchronized keyword. In the first example, we have increment atomic demo class. In this class, we are maintaining an instance of website activity 1. This is the counter. We'll take a look at the implementation of this one. We are using executive service since we want to invoke multiple threads which will be trying to increment this particular counter. So in the constructor, you can see that we are creating an instance of website activity 1 and we are passing 1 million. So this is the count of the number of increments that we want to apply on the counter. And we are also initializing the executive service. So the max thread count is in this case is going to be 100. In the do process, you can see we are trying to submit max thread count threads to executive service. We'll wait for all the threads to complete the execution. So that's the while loop here. Here we have a public static main which is creating an instance and it is basically using get execution time to invoke do process method and we are passing this particular object. And eventually we are using util.getLogger to log amount of time taken to complete do process method. The website activity 1 implements runnable. You can see internally it is using AtomicInteger to maintain the count. In the run method, you can see that we are trying to increment the count max limit number of times, and we are using get and increment method on this atomic integer to increment the count. So let's try to run this and see what the result is. For 100 threads and each thread incrementing it 1 million times, you can see the final count is 100 million and it is taking 1.8 seconds. So we'll just copy paste this into a notepad to compare the results. Let's take a look at the second demo example. It has the same functionality but uses the synchronize keyword. The rest of the stuff is same. We'll look at website activity 2. So website activity 2, you can see it is implementing runnable. It is calling increment max limit number of times, and you can see the increment itself is being protected by a synchronized keyword, and all that we are doing in the increment is this dot count plus equals to 1, and you can see the count is an integer. So let's try to run this and see what the result is. So if you compare this result with our previous result, in both cases the final count is same, so it is incrementing 1 million times, and this is multiplied by a factor of 100 because there are 100 threads. But you can see the resultant time, it is almost double. In this case, using Atomic, we are able to get the whole execution completed in 1.8 seconds, whereas in the second case it is taking 3.6 seconds. So it's a pretty huge performance gain when we use Atomic as compared to Synchronized, which involves locking.